All right. So now just see. So basically, when you're supposed to draw these
Hello.
structures, right? Yeah. Am I audible?
Can you start from the beginning because I couldn't hear you in the beginning and I had to leave the meeting because I couldn't hear you and I
Sure,
didn't
sure,
know
sure,
if you were talking. So,
sure, sure, sure. All right. Now just see. So basically, what happened was, just see. See, let's suppose I'm talking about BeCl2, right?
yeah.
So
Are
now
you writing something? Because I can't
yeah,
see.
you can see. Why?
Uh, okay, you're writing in the corner.
Yeah.
Okay, give
Right.
me one
Okay.
second.
Can you see now?
Yeah.
Okay. Just understand. So let's suppose I'm writing down, let's say BeCl2, right?
Mhm.
So when I'm writing down BeCl2, you understand that beryllium's atomic number is 4. So here the
Yeah.
configuration would be 2, 2. So when here the configuration is 2, 2, so beryllium would have two valence electrons. I hope you're understanding.
Yeah.
So when beryllium will have two valence electrons, so I hope you're understanding that we would have here two electrons. Yes or no?
Yes. Wait, but I'm supposed to draw the okay, okay, whatever. Yeah.
Listen to me. Now, chlorine's atomic number would be 17. So the configuration here would be 2 at 7.
Mm-hmm.
So chlorine would be 1, 2, 3, 4, 5, 6, and 7.
Yeah.
And this chlorine atom would be 1, 2, 3, 4, 5, 6, and 7. I hope you're understanding.
Mm-hmm.
So there would be this bond and there would be this bond. Are you understanding?
Yes.
And there would be this structure. So you understand that there would be beryllium and there would be chlorine and there would be chlorine. Are you understanding my point? Got the point? Yes or no? So you
Yes.
have
Oh, I'm not
the
gonna
central.
be able to respond every time you ask me if I'm under like I am listening, but like I can't like keep saying that I'm understanding after every like
Okay, okay, okay. Got it,
yeah.
got it. Sorry. So let's say we have beryllium, right? So now you have to understand that beryllium is the central metal atom, right? Central metal atom is something. So just hold on to me, just stop me whenever you don't understand. So now I'll be continuing, okay?
Yeah,
So
yeah, yeah.
you
Yeah,
understand.
I understand.
So we'll have the central metal atom. Central metal atom, you understand, is somebody is who is going to give electrons to all the surrounding atoms. You understand? So I would keep a particular element who is willing to donate electrons, okay, and would try and complete the octet for the surrounding atoms. So generally, the central metal atom would be one in number. You understand? The central metal atom would be one in number. Are you understanding? Got it? So when I'm saying the central metal atom would be just one in number, okay, the central metal atom would be just one in number, it would be BeCl2. Got it? So
Hmm.
beryllium chloride is formed. Now, when this central metal atom, look at this. Now, on beryllium, there is no lone pair. Yes or no? On beryllium, which is
There's
my
no
central,
lone pair.
no
Wait,
lone
but
pair
why did
means
you didn't draw the other electrons for chlorine?
I draw. But for chlorine, it is not important. The shape is decided by the central metal atom. I hope you're understanding. The shape
Wait,
is
it
decided
but
by.
beryllium still needs four more electrons, right?
Sorry?
Beryllium still needs four electrons. It only has four right
Four.
now. It needs four more,
But
right?
I'll tell you, this is a octet. This is a octet incomplete compound. And there are compounds whose octet is not complete, yet they are stable. Okay, so I will be
Oh
discussing
yeah,
only the
but we're supposed to complete it. Like that's the point that we like in school we're supposed to complete it and then
agreed,
see if
agreed. Hmm, understand. The idea here is to tell you the geometry, right?
Mm-hmm.
Let me complete this compound. The idea here is to complete the octet and tell me the geometry. But there are certain compounds whose geometry is identified in exactly the same way and they are stable. They may or may not follow the octet rule. So you do not worry about that. This is a stable compound. My idea here is to tell you that whenever you draw a structure, what are you supposed to look into that? Okay, now understand. So let's suppose I'm talking about beryllium. So beryllium will make two bonds. And in the outer shell of beryllium, only two electrons were there. And these two electrons are involved in the bond formation. Are you understanding?
Mm-hmm.
Right. So we would have beryllium, and beryllium would combine with chlorine, and I can see only two bonds being formed. I can see only
Wait,
two
but I
bonds being
still don't understand. It needs. I'm really
Do
confused.
not try and
You're
understand.
supposed to.
Do not try and understand whether its octet is complete or not. If I'm saying that it is a stable compound, consider it as a stable compound and focus on telling the geometry or shape of it. Okay?
Okay.
Now, lone pair would be 1. Got the point? There is no lone pair. So, lone pair here would be 0. Bond pair here would be 2. There are two bond pairs. I hope you're understanding. So, there
Mm-hmm.
would be just two bond pairs. Are you understanding my point? So, there is lone pair 0 and there is bond pair which is 2. So, now you understand that when we have BeCl2, you understand there are two bonds coming out of it. And when there are two bonds coming out of it, always remember when the sum of lone pair and bond pair is steric number, which is 2, geometry will always be linear. The shape will always be linear. So I have to, no matter what, I have to arrange beryllium with chlorine always in the linear fashion and mention the bond angle as 180 degrees from the chart. So you look into the structure, right? Are you there? You look into the
Mm-hmm.
structure and then you identify what is the central metal atom, you identify what is the surrounding atom, and you simply arrange them. That's all. You simply arrange them. And when you simply arrange them in a particular shape, okay, so that would be the
Mm-hmm.
required shape. So you would say BeCl2 is linear in shape. As simple as that. Now, not shape, you will say. If the lone pair is 0, instead of shape, you will use the word geometry. So its geometry is linear. Are you understanding my point?
I don't.
Okay.
Not for linear, but like for 3D shapes, how do you know like which way or like which way some of the um
Bonds.
like not the central atom, but how do you know which way like the other atoms face? Like if they're facing downwards.
It
Like we
doesn't
don't have to
matter.
know the
It doesn't matter.
degrees.
It doesn't matter. It has to be linear. It could be linear like this. It could be linear like that.
No, no, no,
It has to
not
be.
for linear. I'm saying for a 3D shape.
I'm coming to that. One coming. Now let's suppose I have, let's say I have BeCl, BCl3. Here B is boron and Cl is chlorine, right? So
Mm-hmm.
boron is atomic number 5. So I hope you have the configuration as 2, 3. Are you understanding? So boron is atomic number 5 and the configuration here would be 2, 3. So when I say the configuration is 2, 3, so we would have 1, 2, and 3. Are you understanding my point? So when the atomic number of boron is 2, 3, obviously you know that chlorine's atomic number is 17. So configuration here is going to be what? 2, 8, 7. So when the configuration here is going to be 2, 3 and it is going to be 2, 8, 7. So chlorine would be 1, 2, 3, 4, 5, 6, 7. Chlorine would be 1, 2, 3, 4, 5, 6, 7. And chlorine would be
Mm-hmm.
1, 2, 3, 4, 5, 6, 7. I hope you're understanding. So we have this bond, we have this bond, and we would also have this bond. So you understand that you have this particular shape. Are you understanding my point or not? Okay.
Yes.
Now you understand that when we have BCl3, when we have BCl3, you understand? And we we have boron as my central metal atom. So from boron, I can see all the three valence electrons getting used up and three lines are coming out of it. On boron, there is no electron which is left. Are you understanding? On boron, there is no electron which is left. Are you understanding? And when there is no electron which
Mm-hmm.
is left on boron, you understand? On boron, if there is no electron which is left, what would that mean? That, ma'am,
If there's
there is
no electron.
lone pair is zero. Lone pair is zero. There is no lone pair. Lone pair would mean the electron pair which is not a part of both the electrons, which is not under sharing. Do you understand the point?
When you
And
say
here,
lone pair, are you only considering the electrons for the central atom, or also are you also trying to see the
only the central,
electrons for the other? Okay.
only the central atom. Lone pair would mean the central atom electron. You understand?
Uh,
The central atom. The central atom should not contain any lone pair. Now, when a central atom does not contain any lone pair, it would mean what? When the central atom does not contain any lone pair, it would basically mean that lone pair is going to be zero. Correct? Bond
Mm-hmm.
pairs, that means how many bond pairs do we see around boron? One, two, three, four, five, six. That means one pair, second pair, third pair. In each of these pair, I hope you're understanding that chlorine will have,
Wait, so that what electron geometry and molecular geometry means?
yeah, because electrons, if they are becoming, are they, if they are coming in between the two atoms, only then the bond will form. And then these electrons will arrange themselves in a certain direction to form the molecule's shape or molecule geometry. So first, it is important to arrange the electrons in the center, and then obviously the molecule will
Wait, I'm
require.
really what is electron geometry and molecular
There is
geometry?
nothing. There is no called. There is nothing called electron geometry. There is only the molecule geometry. You have to focus on making the bonds as many as possible to complete the octet of both the central metal atom and the surrounding atoms. Necessarily, the surrounding atom should octet should be complete. Central metal atom may
It's
or may not have its octet complete.
it on our lesson, like he told us something about how electron geometry is like related to domains.
That's what I'm saying. See, electrons, see, I'll tell you, do not worry about the words that he's using. First, you understand how to identify the shapes. Do not get the
Wait, because
words
I
wrong.
need to know the words, right?
I will come to those words. Give me time to explain. Give me time to explain. Please understand. Electron domains would mean this area, the common
So
area
that's
here.
one
That's
bond
domain.
is
Domain, yes. So what he's trying to tell you. See, understand. I'll tell you what exactly he's trying to tell you. See, there is electron here, right? There is electron here. There is electron here, right? Electrons are basically negative charges. Yes or no?
mm,
Now, negative,
yes.
negative repels. Negative, negative repels. So he is trying to tell you that when you have boron and when you have these bonds around boron, and before they certainly acquire a certain shape. So you could have drawn these chlorine around boron in any direction. You understand my point? So we would have these electrons and we would have these electrons and we would have these electrons, right? But what is going to
Mm-hmm.
happen that this electron pair, these are two electrons. These are another two electrons. These are another two electrons. So these electrons would do what? They would repel each other. They would also repel each other. They would also repel each other. Are you understanding?
Mm-hmm.
So closer the electrons, more repulsion would be there between them. More repulsion would be there between them. And when there is more repulsion between them, what would happen? They would try to occupy or come to a space where repulsion is minimum. You understand? Where repulsion is
Yes.
minimum. So when the repulsion is minimum, I hope you're understanding that we would have boron and we would have chlorine. So now the bonds start to move away. But obviously, they have no choice but to be connected to boron. So whatever space around boron is available, it would try to get to a maximum distance in that space. You understand? Let's suppose you have a fight with your sibling.
I do understand, yeah.
Got it? So that's the point. So let's say you are in the same room. How far apart you can go? You can go diagonally apart without seeing each other's face because there is only one room to stay.
Oh.
So these chlorines now they try to get away from each other's domain. That's what means by the word domain. So he says that these
So why do
electrons,
I need to know that in order to figure out what shape it is? Like, how do I look at that and know what shape the compound is?
yeah, in the previous class, I told you the same thing that how would you figure it out? So if you look at the data, if you must have taken the screenshots, I've written them down. I told you that if bond pairs are two around the central atom, it would always be a linear shape. If the bond pairs around the central metal atom are three, the shape would always be a trigonal planar shape. Now, if you get a molecule, let's say I gave you an example of BCl3, right? So when I gave you the example of BCl3, what would happen? We had boron, and boron's atomic number would be 5. So configuration would be 2, 3. So we would have 3 electrons, and there would be
Mm-hmm.
chlorine bond with it. You understand?
Yeah.
And when there would be chlorine bonds with it, what would that mean? There would be 3 bonds with it. And
Mm-hmm.
around the boron, on boron, there is no electron which is left. So you have to now remember that if you get bond pair as 3 and lone pair as 0, the shape will always be trigonal planar shape. So we identify a geometry by the sum of lone pair plus bond pair. You understand? Sum of lone pair and bond pair identifies or helps us identifies the geometry. Are you understanding my point? Are you
Mm-hmm.
understanding? Just tell me that.
Yes, I understand.
Right? So that's why I have arranged it in this trigonal planar shape. Now, trigonal planar shape is like A connected to B, connected to B, and connected to B. So I hope you're understanding that we would have this, and this. This would be the shape. Got my point?
But then there's even for, or like, there's three, or there's two or three different types of shapes, for compounds with three domains, right?
Yeah, I'm coming with
I'm
that.
seeing the chart and being a little confused about how to know which one of those three it would be.
I'm coming with that. Did you understand this part?
Well, I mean, I guess I don't because I'm asking that question, but y-
BCl3, did you not understand that it is trigonal planar?
no, because I'm saying there could have been there's other options for it to be, right?
No, there won't be any other option for BCl3. BCl3 will always be trigonal planar because it is
But on
satisfying
the
three
chart,
conditions.
there's like three other ones or something. I remember seeing that.
One second. You switch on the video first.
I can't switch on my video right now
Why?
because like my computer has the sticker over it. Are you asking to see the chart? I can send you a
Yes.
picture of it.
Yes, then.
Okay, give me 1 second.
Are you sending? Yeah, that's what I'm trying to explain you. See, for every lone pair, electron domains would mean lone pair and bond pairs. That's what I'm trying to explain you. What I'm calling as lone pair is that's what they're trying to tell you. That's what I'm explaining you. Let
Hello?
me explain.
Sorry,
Do not
I had to go to
just
another room to take the picture, so I don't know what you just said.
I am saying just let me complete the topic, please. I am coming to every point of it. You are anyway getting panicking about it. Let me complete the topic. I am explaining exactly the same thing. You will understand it by the end of the topic. Please let me explain. I got your point. Do not worry about it now. Okay. But did you understand what BCl3 is?
Yes.
Okay. Now, just do not worry. I'll explain it to you, and I'm explaining it to you with your chart. Wait. Oh, I got really panicky as if something new has come up in that I do not know. Yeah, can you see this chart now?
Hmm.
Now, understand. Now, this is what I'm explaining. I am explaining for all of them. I am explaining this part. Okay. So for every figure, you have to understand. Now, what I gave you the example, understand. I gave you the example of BCl3. Am I right?
Yeah.
Boron's atomic number is 5. Configuration is 2, 3. Boron has 3 electrons here. It formed bonds with chlorine. Chlorine's atomic number is 17. Configuration is 2 at 7. So chlorine kind of formed the bonds with this like this. You understand? So chlorine forms the bond like this. 1, 2, 3, 4, 5, 6, 7. And it would make the bonds. Are you understanding?
Yeah.
So boron will form 3 bonds or not?
Okay.
Now, when boron forms 3 bonds, do you see any extra electron remaining spared on the boron atom? Do you see that?
No.
No. That means around boron there are all 3 bond pairs, yes or no?
Yes.
Now, when there are all 3 bond pairs, it becomes this perfect case. In this perfect case, what is happening? That ma'am, only there are 3 bond pairs, yes or no?
Yeah.
And when there are only 3 bond pairs, that would mean that bond pair is 3, lone pair is 0. So the sum of lone pair plus bond pair is 3. This is what your chart is saying is electron domain. That means this is basically the sum of lone pair plus bond pair. Got my point or not?
Mhm.
Okay. So whenever the sum of lone pair plus bond pair, which your chart is calling as electron domain, is 3, the shape always comes out to be trigonal, planar, and the angle would always be perfectly 120 degrees. Any doubts on this? Just tell me.
No.
Okay. Now let's take a case of Let's take a case of uh, SO2. Okay, SO2. Now, when I take a shape of a case of SO2, now take an example. In SO2, what is going to happen? We would have sulfur. Sulfur's atomic number is 16. So its configuration would be 286, right? So
Mm-hmm.
sulfur would have 1, 2, 3, 4, 5, 6. Yes or no?
Yeah.
Oxygen's atomic number is 8. Configurations is 2, 6. So what is going to happen? Oxygens would have 1, 2, 3, 4, 5, 6. And there would be two bonds here. And like this. Because the sharing would be something like this. The sharing would be something like that. I hope you're understanding.
Yes.
So we would have this part. Yes or no?
Mm-hmm.
So we would have sulfur dioxide formed like this. But on sulfur atom, two electrons pair. That means two electrons would stay the same.
Okay.
So we have these two electrons. Are you understanding? We would have these two electrons. So now realize the case that from sulfur, which is my central metal atom, and two oxygen atoms becomes my surrounding atoms. You understand? So we
Mm-hmm.
would have the central metal atom and we would have the surrounding atoms. What would happen? What would happen? That the central metal atom that we have, okay, it would have a lone
Yeah.
pair. So now take the case that from now, whether it is a double bond between the two atoms, here you must be able to see the double bond, if I'm not wrong, right? A double bond here. This double bond
Yeah.
would be counted as a bond. That's a bond between them. Okay, that's a bond pair. It's a bigger bond pair, right? Doesn't matter how many electrons are being shared between them. Here we have four electrons. Doesn't matter, but it is between the two atoms. And hence, when the central metal atom is one, surrounding atoms are two. That's it. Irrespective of the fact whether they are joined by single covalent bond or whether they are joined by double covalent bond. Are you understanding?
Mm-hmm.
Right? And then it has a lone pair. Now, how many lone pairs do I get to see in the structure? One. How many bond pairs do I get to see in the structure? Two. One bond on this side, one bond on this side. Any doubts on this?
No.
Right? And when I have this, the steric number here would be 3. Got the point?
Yeah.
Whenever the steric number is 3, you are sure that there would be along the three lines. That means the geometry would be trigonal planar. That's the geometry. So what do? You put double bond O here, double bond O here. But you know that there is no third atom around sulfur. So on this direction, you will simply put a lone pair. Am I right?
Mm-hmm.
So now, what is going to happen? So the way your diagram has explained it, it would be like this. On this line, you would put a lone pair. Now, the lone pair is actually not counted. So now it would have been a trigonal planar geometry. It would have been a trigonal planar geometry if in the place of lone pair, also we would have another atom making a real bond. But here we do not have any real bond. You understand? So we would have simply sulfur. We would have a double bond O and we would have a double bond O. Yes or no?
Yes.
We would have a double bond O, and in place of this, we would have a lone pair. That means the three positions that were allotted for the geometry to be trigonal planar, out of these, only two places have atoms and one place has lone pair. So now, if we, let's say, we hold on to and we hide the lone pair, what shape does it look like? It looks like a V shape. If I hide the
Okay.
lone pair, what shape does it look like? It looks like a V shape. So I would say that while identifying the shape, while identifying the shape. Okay?
Mm-hmm.
While identifying the shape, it would be a V shape.
Yes.
You understand? But its
Yes.
possible geometry would have been trigonal plane. So this SO2 example is this domain. But here also lone pair is 1 and bond pairs are 2. So steric number is 3. So with electron domain 3, it is saying that there are two possible types of structures possible. Either around the central metal atom, all the bonds would be present, or in place of one bond, there would be a lone pair. Are you understanding my point? And when there
Yeah.
would just be a lone pair, it would mean that the shape, it would have now two answers. One, you will tell the possible geometry that it could have and the shape. Are you understanding?
Yes.
Any doubts in this system?
No.
That's what I was trying to explain you, that please listen to me. I'm coming to that. Got the point?
Mm-hmm.
So this one was regular geometry that I was saying. And I left the last lesson at a point where I said that I have completed the regular geometries. I will explain you the distorted geometry. So this is a distorted geometry. Now in distorted geometry, what exactly is going to happen? I will explain you that. Did you understand my point up till now?
Mm-hmm.
Any doubts in this?
No.
Got it? Sure.
Yes.
Now understand. When I have sulfur, we would have SO2 and we would have this lone pair. Yes or no?
Mm-hmm.
Now, understand. When we have sulfur and oxygen and we have two electrons in exactly between them, right? So we would have this. So we would have one, two, three, four. Are you understanding? So here we would have sulfur's nucleus and here we would have oxygen's nucleus because both the atoms would have their nucleus. I hope you're understanding. Are you understanding?
Mm-hmm.
So both the nucleus would apply their force of attraction on these electrons, which are being caught up in exactly between the two. When both the atoms are going to apply their force of attraction, okay, these electrons would not be able to move on the either side and they would just be stuck up exactly in the middle. But if
Okay.
we are talking about a lone pair, now this lone pair is basically exactly on sulfur. This lone pair is exactly on sulfur. So that means only sulfur's nucleus is exerting the force of attraction on the sulfur. You understand?
Mm-hmm.
So only sulfur would exert its force of attraction on the sulfur atom. That means when you have this set of electron pair, when you have this set of electron pair on the sulfur atom, okay, so there is a force of attraction on this electron, and only one nucleus is attracting it. That means on the lone pair, the force of attraction is less than the force of attraction on bond pair because on bond pair, the two nucleus is exerting the force of attraction. But whether it is lone pair or whether it is bond pair, both of them are electrons. So the charge on both of them would be negative. So do you realize that this negative charge and the negative charge here in between, they would have some repulsions. So book states that there is a repulsion between the lone pair and bond pair. Are you understanding? Book says that there is a repulsion between the lone pair as well as the bond pair. Got my point?
Mm-hmm.
And when there is a repulsion between them, here this repulsion and here lone pair is even free. This lone pair is free. You understand?
Mm-hmm.
And when this lone pair is actually free, what is going to happen? Just tell me. When this lone pair is free, what do you think is going to happen? Tell me.
Um,
We have this. When this lone pair is free, this is actually going to push the two bond pairs closer. So rather than being at 120 degrees, they would come closer and we would have this lone pair. I hope you're understanding.
okay.
So that's what it is trying to say, that this bond angle here, because of the lone pair out here, because of this lone pair, because of this lone pair, you understand? This would
Yeah.
be closer. And obviously, when they come closer, why? Because the lone pair wants to just occupy all the space. Lone pair wants to expand. And why lone pair is capable of doing that? Because lone pair is not being held in its place with strong force of attraction. I hope you're understanding.
Okay.
Got the point
Yeah.
or not? So we would have this electron there, and kind of put the it would kind of put the electrons here. I hope you're understanding.
Mm-hmm.
So this is the case. Understood my point or not?
Yes, I understand.
Better. That's what the case is.
Yes.
So whenever on the central metal atom there are lone pairs along with the bond pairs, that kind of geometry would be called as a distorted geometry. But to identify the distorted geometry, you should have an idea of the regular geometry. Regular geometry does not have lone pair. Are you understanding? Regular geometry does not have
Yes.
lone pair. Are you understanding my point?
Yes. I have to leave like a few minutes early if that's okay.
I do not mind, but is this topic clear to you?
Yes, yes, I understand now.
Okay, great. Now, next topic, next part. Now, when we are talking about the CH4 part, just understand. When I'm talking about CH4, you understand carbon's atomic number is 6, right? So configuration would be 2, 4. So carbon would have 1, 2, 3 electrons, 4 electrons. So when I say carbon would be 1, 2, 3, 4, what would that mean? It would be hydrogen. It would be hydrogen. I hope you're understanding. So we would have this, we would have this, we would have this, we would have this. I hope you're understanding. And because carbon is kind of completing the octet for hydrogens, it would also need all of them for carbon. So I hope you're understanding that you would have carbon making the bonds of hydrogen. Are you understanding my point?
Yes.
And I hope you're understanding that when we have CH4, how many bond pairs do we have around carbon? Tell me.
4.
How many lone pairs do we have around carbon?
0.
0. What is the sum of lone pair plus bond pair?
4.
The sum of lone pair and bond pair is called as electron domain, or what you call as this. That means these electrons. Now, all of these bonds are exactly the same if you focus on them. So, around carbon, they would try and occupy the maximum possible distance, the maximum possible angle. So, this maximum
Wait, so is
possible
it a
angle,
tetrahedral?
yes, that's theta here. And here the angle would be a perfect 109 degrees and 27 minutes. And your
Okay.
books have not mentioned minutes to be more precise. So they've just mentioned 190.
Okay.
All right.
Yeah.
And
I have
every
to
angle.
go right now.
Sure. Fine. So we are having
Um,
a 50 minutes of class.
what?
We are having 50 minutes of class.
Yes, I think so.
All right. Sure. No worries. When
Oh,
will be
I
the
don't
next
think it
class?
was 50 minutes. I think it was like because we started
I don't
at
remember.
38, I think. So that's 22 plus 25. Oh yeah, basically. I don't know. Yeah, that's 50 basically. Sorry,
Oh,
what were you saying?
okay. So this would be CH4.
Yeah.
This would be a tetrahedral shape, right?
I have to
Now, if this is
go.
a
Hello?
okay, fine, fine, fine,
Yeah.
fine. So when are we having the
Um,
next class? Just tell me.
next class, I'm not sure. I think probably just like next week during the weekend.
No problem.
Yeah. Okay.
All right,
Thank
bye.
you. Bye.